get started with a 45-minute discussion on radiation detection, radiation sources, radiation signatures. Please, again, as always, feel free to ask questions, especially as it pertains to the group project. So, what I want to do is assume and hope, but I'll assume you read pages at the end of Professor Pruson's notes, pages 33 and 34. It goes into a discussion of radiation and biological effects of radiation. I want to pick up at the beginning of that on page 33 because Professor Pruson discusses the heat sources and forms of radiation. So let's start there. Actually, let's back up a step. Radiation detection in national security applications, I think it's obvious in this class, it's going to be related to verification, determining the presence or confirming the non-presence of radioactive materials, including special nuclear materials. It's clearly important for national security and homeland security applications and radiation detection. After 9/11, there was congressional mandate to put radiation detectors at ports and entryways in the United States. So that's its own challenge. And although it may not have a direct relationship to the particular group project this year, I think it's really an interesting policy and technology problem, and it would be good to understand it. I think hopefully you'll get some basic understanding of that today. And of course, for radiation safety and protection, detection is important. So let's start with the idea that you have special nuclear material as a subset of radioactive material. It can decay by various mechanisms. We've discussed those a lot. We discussed spontaneous fission. In an earlier discussion, we talked about decay by beta decay and alpha decay. So let's talk about those radiation sources. I left it off of here, but let's get out of the way real quick. Let's talk about the ionizing radiation. Again, what's important about the ionizing forms of radiation, especially with regard to detection, is that they will lead to the creation of ion pairs in a material that they're interacting with. They're energetic enough and have the right wavelength, like we discussed in the first class, that they'll create pairs of positively charged ions and free electrons. Now that's important. It becomes crucial to the detection process. And Professor Pruson's write-up of biological effects, of course, that's central to biological damage, the creation of free radicals and all the chemical reactions that now happen when you have charged particles floating around. And the key point with regard to the biological effects as well as radiation detection was what? What's the key feature of, say, an alpha particle that makes it such a damaging biological agent? It leads to create so much biological damage. An alpha particle is a charged particle that has a charge of what? +2, and an electron has, a beta particle is basically an electron. So the charges aren't that different, but there's something really important and different between those two particles. And it's the size, yes, and that's related to the stopping power, how quickly they stop. And the stopping is based on the Coulombic interactions between this charged particle, either the heavy positively charged ion or the electron, the Coulombic interactions between this particle and the surrounding electrons. So now already you should be thinking one of the key features of the stopping medium, whether it's a body or a detector, is the electron density, right? The number of electrons per, say, volume or mass of that material. That's going to help determine how quickly the particle stops and imparts its energy to the medium. Why is that important? Because a high density of energy imparted to a biological entity like cells will create more damaging effects. So you have this issue with alpha particles have very high biological damage. Beta particles are not as damaging. And so what can we infer then about the range of these particles in the medium that they're interacting with. The alpha particle range is going to be very short, right, okay. And so I'm going to segue this all to the detection, and in a way I am really trying to get alpha and beta out of the way, because when it comes down to it, their ranges are very short. And so standoff passive detection, standoff meaning I haven't gone and taken a swipe on the surface and I'm not putting that swiped swab into some mass spec machine or some analyzer or some detector, and it's coming in intimate contact with it. But instead I'm standing up and I'm counting on the radiation being emitted by the material and waiting and hoping and needing for it to hit my detector and interact with my detector from a distance. So when it comes to standoff, and I use the word passive, what do I mean by passive detection? What would be an example of non-passive detection?
Radar. It's something that emits.
Sure, yeah, it sends out a reference signal and you wait for a return signal. X-rays would be non-passive. Or in this line of work, you can think of, say, neutron activation, where you bombard a material with neutrons and you look for certain signature reactions, which will emit. In the signature, of course, is the gamma rays that they might emit. You look for those. But let's narrow our discussion for the group project for homeland security applications to standoff passive detection. Alpha particles. What's the range of an alpha particle in water? It's in the write-up. It's a good rule of thumb to have. And once you have that, you can start to scale it. So let's look at it this way. If I have an alpha particle source, even if it's energetic, 5 MeV, and I put it in your hand, do you need to worry about it damaging your hand? The answer is no. Let's go ahead to a graphic on that. You see, I didn't make up that hand thing. The internet is rife with hand dose images, and I chose one from a government. But I actually like this one. Gamma rays are not energetic. I mean, alpha particles will not penetrate the outer layer of your dermis, right? Okay. The range is on the order of tens of microns in water. If I scale water to air, what's the difference in density? This is a good rule of thumb thing to know. What's the difference in density between water and air, roughly? What's the density of air? Roughly 1 kg. That's good. I can't convert that in my head. I'm going to hope that comes out to 1/1000th of a gram per cc. So that's roughly what it is. And water is 1, air is 1,000. It's approximately a 3 order of magnitude difference between them. Remember, alphas are primarily stopping due to Coulombic interactions, right? So we can scale ranges roughly by density, because density is going to be a good proxy for electron density. So if an alpha is going a few microns, a few tens of millions of a meter in water, it's not going to make it through the dermis in your skin. In air, it might go what? A few tens of millimeters, right? Maybe a couple centimeters. So boom, we're done with alphas in a way for this discussion, because we just determined, even if I had a hot, fair alpha source sitting right over there 10 feet away from me, and I had some kind of great charged particle detector, very low probability of seeing alphas from that source, simply due to the attenuation in air alone, because these are big, heavy charged particles that deposit all their energy within a few microns in water or millimeters in air. Beta particles, right, or the equivalent of electrons that are emitted from the nucleus when a neutron decays into a proton. We talked about that. Of course, a neutrino comes off. Let's not get into neutrino detection for this discussion, albeit it is an interesting application in some very interesting non-proliferation and verification applications, and it's not something to totally dismiss, but not to discuss for this discussion. Beta particles have a longer range, but still not long enough to be a significant source for passive standoff radiation detection. A few millimeters in a substance like aluminum, let's scale that roughly by 3,000, it's going to be a few, what is it, on the order of a few meters in air. Again, not a robust source for passive standoff detection. And the key thing there is these are two particles, or charged particles. They're interacting strongly with the electrons in the medium, and they're stopped relatively close to the source. Now, let's move on to gamma rays, because of course that's where the discussion of standoff detection really begins. Gamma rays, charged or not charged? Gamma rays are not charged particles, right? They are electromagnetic radiation with sufficient energy to interact with the nucleus. So someone give me an example of what's one of the reactions. This is page 34 in Professor Prusen's write-up. It's really nice discussion of this in plain language. I'd encourage you to read that if you haven't. Give me one type of interaction between a gamma ray and a stopping medium. Pardon? I think gamma rays are reflected, but let's talk about interactions that create ion, that give it this name, ionizing radiation. Let's talk about the types of interactions that give rise to these ions, because these are really all we have to hold on to in so many cases to detect this type of radiation. So think about solar panels. What's the basic phenomena you're taking advantage of in a solar panel? Photoelectric effect. Okay, so a gamma ray can come in and interact directly with an electron in the material. The electron can absorb the photon and be emitted. Beautiful. Now you have, hey, it's how solar panels work, right? You have electrons being free from atoms. You put a field across it. You can collect the charge and make a current. That's the same idea in many detectors. You can have inelastic or incoherent scattering of photons, where they come in and give enough energy to an electron. The electron bounces out at some angle, and a residual gamma ray is emitted as well. So you can have, it's sort of a hybrid. You can have high energy gamma ray interactions with nuclei that result in production of pop. Beautiful. So if you know that much, so what's the cutoff energy for production? No, yeah. Well, no, twice that, right? Because you're making two. It's a beautiful thing. There's no matter, and all of a sudden there's matter, and energy got turned into matter. The rest energy of an electron or positron is 511 keV. So if you're going to make two of them, your gamma ray needs to have at least 1022 EV coming in, so you can at least have enough energy to make these two particles. And that's a beautiful thing, right? Because there's your free electron, which you can try to detect. And by the way, when your positron eventually finds another electron and destructively combines, you'll have what? Right? You'll have completely oppositely aimed zero momentum gamma rays coming out. So you have multiple signals for that. But the point is, unlike alpha particles and beta particles, gamma rays, although they can interact many different ways with material, have a much longer range in air and in low Z materials. Most of these phenomena, they're interacting with electrons or the protons in the nucleus. So unless you have high Z materials, the probability of interaction with gamma rays materials is relatively low. Let's talk about that briefly. This is a nice paper I found referenced at the bottom. It's a little complicated, but on the left is a comparison between carbon and lead. Right? Lead is your classic gamma ray shielding material. But for both materials, what the chart's showing you is the relative contribution of the different types of interactions between the photon, between the gamma ray and the material at different gamma ray energies. So you can see at relatively low energies, an MeV and below, the effect might predominate. At around an MeV, Compton, the incoherent gamma ray scattering might predominate, but you can still have photoelectric effect. And as you get to higher energies above roughly an MeV, 1000.022 MeV, you're physically allowed to start having pair production. As Professor Prusen used to say to me, everything that can happen will happen, just in different amounts. And that is really the beauty of what this chart is showing. All of those cross sections, meaning all the probabilities for all those interactions happening, combine to a total interaction cross section. My reaction when I looked at this, by the way, is you go, oh, you know, lead's so good, everything's got to be shielded with lead. But then you look at the attenuation coefficient, right? The attenuation coefficient, right? So the intensity of my beam at any depth into my reference material is proportional to the initial intensity of the beam. So if I'm shooting a beam of gamma rays into the material, at some depth x, let's say this is the intensity, the number left, at some depth x is equal to the initial intensity, E times E to E, mu, the attenuation coefficient, times a depth into the material. So this is a chart of that attenuation coefficient. Notice, and you'll see this a lot, it's very useful actually, it's expressed in centimeters per gram, so it's been corrected for the material density. And that's important. Because if you look at this, you go, wow, lead's better, but it's not like 100 times better than carbon. Nobody tells you should shield a hot cesium source with a nice light carbon or graphite pig. It's called a pig, big honking source holder. But that's because density has been taken out of this equation. So say at a couple hundred keV, say 0.2 MeV, you can see the total cross section for carbon is on the order of 0.1, a tenth centimeters squared per gram. The same point for the lead, maybe it's a factor of 5 greater. You see, factor of 5 is not that big. Not until you take into account the density of lead is so much greater as well. And lead is about 11 grams per cc. Carbon, depending on the wind form, can be relatively low, single digits. So that's the idea. What I wanted you to understand here is that the attenuation of gamma rays in material depends upon the gamma ray energy. Because at different energies, you can have different types of interactions. All those interactions combined to give a total attenuation coefficient. And in our case, the ones we're really interested in are the types of interactions that give us free ions, because that's what we can collect, just like a solar panel collects charge, detectors collect them. We'll go over some of the methods real quickly after this. But you can see on the right, I like this diagram. It shows you the basic idea of some of these interactions. Photoelectric effect, gamma ray in, single neutron totally absorbs the gamma ray and is emitted. Compton effect, C, I'll go down to the crust. Compton effect is incoherent scattering, gamma ray in, and you get gamma ray and an electron out. And then pair production, E, is the one where you have a very energetic gamma ray in. And it's so energetic, all it has to do is interact with the nuclear field in the nucleus. It doesn't even, it's not like it hits an electron and knocks one out. It is actually converted into an electron-positron pair. And we don't need to, we don't need to worry about photonuclear for this case. Although, if I could tell you that you could shoot direct a very intense beam of high energy, say, 12 MeV photons into a nucleus, and that would induce fission, which sort of makes sense. I mean, what's the binding energy of a nucleon? On the order of 10 MeV. So you turn on, you give the nucleus enough energy on the order of the binding energies, something could happen where a nucleus either splits like fission or emits a neutron. But if I were to tell you that you could put a high energy beam in and get signature radiation out, what would that be an example of? Passive, or that'd be a form of active interrogation, which is which is a real form of interrogation. I don't think it's been commercialized yet, but it's an interesting area of work and research. So we have alpha. Interesting, especially if you're taking swipes and can get in direct contact with the material and analyze it, but not interesting for stand-up. Beta, very similar. Unless you're in a laboratory environment, probably not a good form of detection to try to confirm or the presence or non-presence of material, to try to monitor material in a facility, to try to detect it on its way in or out of areas where it shouldn't be. You're probably going to rely on gamma rays or the last form of ionizing radiation. Oh, I don't have a chart on this. Would be what? So neutrons, of course. All right. Now, how do neutrons create ion pairs? They're not charged particles. They're not gamma rays. In what way do neutrons potentially lead to an ion pair? That is, do something where they create, they induce a electron to leave a nucleus or a nucleus to leave an electron. How is that happening in this case? Okay, so neutron, we typically think of them, right, elastic scattering is the first thing that comes to mind, especially when we talk about reactors. Of course, we have fission absorption, that's one. And you can base detectors on coating the inside of the detector with fissionable material. So you could always use fission reaction. So that's not what you said scattering. How would a scattering event give you a charged particle pair? That's it, yeah. So if you get an energetic enough neutron, say fission energy, few MeV neutron, to be incident on a nucleus, it can hit it hard enough to separate the nucleus and the electron, and you have an electron pair. So that depends on the kinetics of this elastic collision. So it's a billiard ball type collision.
Can a neutron interact directly with an electron? It can't be.
No, there's no Coulombic interaction. That's beyond my expertise. That I couldn't say. But for these purposes, it's not a phenomenon that really affects the interaction of the neutron with the material in a way that we detect it in common practice. But a neutron can induce fission, which gives you a lot of energy in ions coming out. It can have a elastic scattering on a nucleus that gives you an ion pair because it hit it so hard it pulls apart from. It can be absorbed, neutron activation, right? And so what happens when a nucleus absorbs, say, a thermal neutron, and it now has all this excess binding energy? It may have many MeV of excess binding energy because it just absorbed this extra neutron, and now it will de-excite through various. It depends on the nucleus. It will de-excite through various mechanisms, and that includes gamma rays. And there are signature gamma rays that you, as a spectroscopist, can say, hi, that goes with neutron capture on this material, that goes with neutron, that energy, and it sort of becomes a fingerprint. I'll show you an example in a second. I think a key takeaway is to understand that in all these cases, you're really not detecting any of these particles directly. You're detecting the ion pairs that they create. And even in some of those cases, you're not detecting those directly. Let's go back for a second and talk about, I skipped this chart. Let's talk about the source itself. And the types of gamma rays that we're talking about coming out of the materials we're most interested in. The source term. We won't get into how this spectrum was measured, although it's very interesting. But let's just talk about the features of the gamma rays coming off the materials that we care about. So this is a high-resolution gamma ray spectrum from some mass of 93% enriched uranium. That is uranium that's 93% U-235 and 7% not U-235, U-238. Although with some U-232 content. And this is from a publication by just a great mentor and scientist and gentleman named Tom Gosnell. And what I want you to understand from this are a few things. One, you can see that any given material is going to be made up of a composite of multiple isotopes. Not all the time, but almost all the time. Each material emits gamma rays that are distinct to those the nuclei in that material. So you see in the zoomed in region in U235, there's a 186 keV line, right? That is a distinctive gamma ray from U235. Now, how you measure that fine enough so that you can discern that energy gamma ray from one very close to it is the art of building and operating detectors. Look at the uranium-238. Oh, well, by the way, where are those gamma rays coming from? What's happening in the uranium that's giving us this? Is it spontaneous fission? It's other forms of decay. Yeah, it's not a. I just want to get them. These aren't fission products, or these are directly from the other paths of decay for the U235. So here's a question I want you. If you know it, don't blurt it out, because I want this to be like a pseudo homework. It'll be a long time until we get to discuss this again, probably a few weeks. But look at the uranium-238 portion of the spectrum. I mean, it doesn't typically look like that, right? I mean, Tom made this nice chart as to be educational. It's not nice and color-coded. It doesn't just tell you this portion from this isotope. But I want you to look at the U238, right around 1,000 keV, right? An MeV. You see that peak? That's a very, it's a distinctive peak that tells you you're likely to have uranium-238 present. Whether you're at a foreign facility and you're confirming the material they say is there in the certain quantities, or whether you're monitoring the traffic, the cargo container traffic coming in the port of Oakland, or you're cleaning up a site for some kind of accident, and you look for certain energy gamma rays. My question to you for next week or weeks is, where's that gamma ray coming from? What isotope? Is it uranium-238? Go look up the characteristic gamma rays for U238. Is there a 1001 or 1000 keV line associated with U238? If there is, that's easy. What's going on here? Do the same for the 186 line. And then let's discuss that. And you can understand that gamma spectroscopy, the art of trying to verify what materials are and aren't present, is more than just looking for the specific isotope that you've been told to look for. Because you have to take, I'll give you a hint, you have to take into account all of the decay products. And when the decay started and when isotopes start building in, start understanding radioactive daughters and buildup. Something to keep in mind when I come back and ask you, okay, who's got the answer? Where's that 1000 keV line coming from? It's an interesting answer. And I want you to contrast it to the 186 line. Okay, so we have material of interest. It's emitting alpha particles and beta particles, but the ones we can see at meters distance are gamma rays. Let's go back, and neutrons. The alpha can't make it through a piece of paper. The beta can't make it through a little bit of thin aluminum, but the gamma rays can. You need a lot of high Z material, high Z. Z being the atomic number of protons, or in this case, I'm thinking the number of electrons, but same idea, right? You need a significant amount of high Z material to stop the high energy gamma rays. Oh, no, let me ask you one other thing to add to that reminds me. I keep saying gamma rays. Is it all? Am I 100% sure that we're only looking at gamma rays on this chart? So I'll add a third thing on there. Tell me what are the characteristic X-rays for let's call it for enriched uranium. If I said, you know what, all I have is a detector, it's some weird detector and it knows the difference between gamma rays and X-rays, and what gamma rays what X-rays am I looking for, and where are they coming from? What's causing the X-rays?
I don't know if you mentioned earlier, but what's the detection scheme? How do you measure?
Good. That's a great segue. Let me answer that with let's cut to a simple diagram. That spectrum was measured with a germanium detector, which is in a way very close to what I was describing like a solar panel. It's a solid chunk of semiconductor-like material. And although this diagram is showing a gas-filled ion chamber, it's a very similar idea. In that case, radiation comes into this material, say a gamma ray. It can interact through photoelectric effect, Compton scattering, pair production if it's high enough energy. It does one of them. Let's say it's Compton, and there's a Compton electron that's now running free. It's been given enough energy to be free from its atom, and it's free in this chunk of germanium. The germanium is held under an electric field, so you can collect the charges and measure the current. It's like a semiconductor, and it measured current. And you do a lot of hard work in design, and you work the electronics so that the signal that comes out, the electrical current signal that comes out, is proportional to the amount of energy that went in. And that's really important, right? And you get your signal. Now that's a solid state detector. Let's talk about this, a real simple case of a gas-filled detector. You take say a metal cylinder, and you have the cathode at the outside, and you have an anode wire running down the middle, and you fill it with some kind of gas that you can pressurize it to increase the density of the material in there. What's a typical fill gas for, say, a simple Geiger counter? You got the engineering students know that? What is a fill gas for a Geiger counter? Argon. Why? Is it so you want a noble gas so it doesn't like interact with the tube and corrode it and various things? So the gamma ray comes in, or maybe the beta particle. I guess you have. I mean, in some cases you have the beta particle penetrate. Maybe, I don't know. It's not an alpha particle. It interacts with gas, creates ion pairs. There's a charge, there's an electric field between the anode and cathode. Those connect out to some fancy electronics. You collect the current. You know you just had an interaction. That's the basic idea.
Does this also measure the spectrum?
No, well, great. So we don't have a lot of time left, but we don't have much left either. No, so in this case, let's assume it doesn't, because your voltage is so high across your anode and cathode that, let's assume, in the simplest but most robust case, it's basically when a charge comes in, it's like hysteresis. You're putting so much voltage across this that all it takes is a little bit of extra ion energy, and all the gas just cascades down. Like one electron pair is created, that electron pair splits, and those now you have a new nucleus being pulled in. Now that hits another nucleus, and that one branches out, and all of a sudden you just have a big signal. That's how Geiger counters work. The signal is immediately quenched, and all it tells you is yes, no. The gas either went or it didn't go. Went meaning it just went all ion pairs, and you got a big spike signal, or it didn't. What do you know from that? You see a signal, you have no idea what the energy particle was. Okay. Now there's various engineering methods you can do, and I don't have a second diagram, but imagine a similar detector where you've engineered the electronics so that the number of ion pairs created is proportional to the initial number of ion pairs created. That's a beautiful thing. It's called a proportional counter. And now you've done this work. You've created these grids around the anode to try to slow down this cascade of electrons, things I've read about, but I could hardly imagine how you engineered it in the first place, but you've done it. You've created this grid around it, and now you get a signal that's bigger for if there was more ions created in the first place. Now your signal is proportional to the incident energy, or at least to the energy deposited, and that's the key. That's a big step forward. You detect neutrons primarily with a helium-3 proportional counter. What's the method by which we put helium in a tube and detect neutrons? So I lied to you before, right? We talked about neutrons and we said, oh, it's scattering and proton recoil, fission. There's another thing that you take advantage of. What's the whole basis of a helium-3 detector? A helium-3 based neutron detector. It's that helium-3 has a significant large cross-section, meaning probability for a reaction type, a large probability of interacting with a thermal neutron to create, and it's an NP reaction. An alpha reaction? My gosh, it's been a long time. But there's a probability for the helium-3 to absorb a neutron and give off a tritium and a proton. Yeah, that's it, right. And so you can take advantage of certain nuclear reactions. And I don't mean nuclear reactions like nuclear fuel. It's not fission. It's a specific type of nuclear reaction where a neutron comes in and it induces the helium nucleus to split into a proton and a triton. Triton is what? What's tritium? Tritium is what element? It's the triple heavy form of hydrogen. So in that case, the particle comes in this case, say a neutron interacts with the helium gas. The helium gas absorbs the neutron, splits into two charged particles. You collect them in a proportional tube and use various means I said proportional. You don't get neutron spectroscopy out of that because all you're really measuring, all you could possibly measure really is the energy of that reaction. That's going into too much depth, but you at least know you detected a neutron. I'd be remiss in the few minutes I've left. I know you guys, you've had a long evening here and we have 5 minutes left, but we've got to talk about gamma ray detection through scintillation. So I mentioned before that in some methods you get to collect the ion pairs directly and measure them as an electrical current. That's the beauty of, say, a germanium detector, semiconductor-based detectors, where it's solid state and you have a charge across it and you just collect. Even the proportional counters or the Geiger counters are like that. You create a charge and you just collect it in your field. There's another method in which you take advantage of the fact that certain types of crystals will de-excite by emitting visible or near visible light. So you use that crystal as your interaction medium. The ionizing radiation comes into the crystal, creates an ion pair, an electron, say, or an electron goes flying through the crystal, and yeah, you have this excited, positively charged nucleus, and it's depositing energy in your crystal, and the crystal will then absorb that energy, but will always de-excite at certain frequencies, which are near or close to visible light. So all you have to do is put a photomultiplier tube basically looking into your crystal, and what is it looking for? It's looking for basically flashes of light. That's fine. What does it mean for a photomultiplier tube to look? Well, it's a photocathode connected photomultiplier tube, meaning the whole job of the photomultiplier tube is to convert flashes of light into cascades of electrons. Again, I don't know all the engineering. It's amazing to me that it's beautiful engineering to devise materials that are light sensitive and can be configured to emit electrons when bombarded with certain frequencies of light, and then to control that cascade of electrons to be proportional to the incident energy, which again is the key thing. If I bring in a gamma ray and I deposit 1 MeV of energy into the crystal, I see a bunch of flashes of light, and I get a certain current out, current, whatever the measure is. Then I hit it with a 2 MeV gamma ray. I see twice as many flashes because I have some great crystal. It's perfectly proportional, but my photomultiplier tube only gives me 75% more current. Well, I'm not in a very proportional state right now. My spectroscopy is all messed up because nature's giving me twice as much energy, but my signal's only coming out with, say, 75% more. And that, of course, get back to the whole point, is going to significantly degrade the resolution of gamma ray lines in your spectrum. Your ability to look at, oh, that's the 185.7 keV line from uranium as it would exactly be predicted from physics, isn't going to look like a nice line with a very small full width at half max, right? I know the nukies know that term, but you measure a peak, full width at half max. What's good resolution? Like 3% or better? That's accepted pretty good. If your detector isn't proportional, if the signal is going to change for the same incident energy, you're going to have very poor resolution. You might not be able to discern a single line there. You may have spectra that instead of being nice discrete peaks, just look like big smush humps, and spectroscopy becomes more difficult. So in one final thought then, we have these, we talked about sources of radiation, and I want you to think a little bit more deeply about that in the 1000 line from uranium. We talked about stopping an interaction in matter and how the interactions are detected in detectors. I won't go into ranges too much. This is actually a nice graph. It shows you that on a per gram basis, the absorption coefficients in different materials can be very different or quite similar depending on the incident energy of the photon. And that's important to keep in mind. Here's what I want you to keep in mind finally, because this, I think, really gets to the practical aspects of your semester project. What are the real world difficulties of verifying, detecting materials passively and from a distance? Well, we already talked about attenuation of signal, right? And if it's an alpha source a few meters away, the air alone is going to attenuate it. Here I've plotted, and this is me just taking the the nuclear interaction data files, and just plotting them basically, and showing the neutron mean free path. What's the mean free path? The average distance a neutron will go before it interacts. The neutron mean free path in air. So, and what was the energy of a fission neutron, roughly? Give me a ballpark. A neutron is born at blank energy. Pardon? Yeah, a few MeV, two, yeah. So I should have plotted it better, but that's what it appears. So you can see, if we think if we're concerned about a material that undergoes spontaneous fission, might be popping off fission neutrons, and we're going to take a helium-3 detector and look for neutrons. You can see we have a standoff to hundreds of meters, would be probably too much, right? But a few tens of meters, attenuation is not going to be an issue. Why is 100 meters probably less feasible? Well, let me rephrase that. If 40 meters might not attenuate a 5 MeV neutron very much, right? We might have 90, I'm going to make up a number, 95% of our neutrons emitted would still be reaching us uninteracted. So the air wouldn't be the problem. What would be the problem as we got out to many tens of meters? I had it up on the slide before. It's 1 over r squared, right? I mean, you have to take that into account, right? And so you guys know this, right? You have a point source, and all the radiation is being emitted out into 4 pi steradian solid angle, right? The intensity per some unit area on any surface at a given radius is going to drop off with 1 over r squared. So I take that same area and I put it close in. It has many ray traces of radiation passing through it. I take it and put it much farther out, and it's a much lower probability of detecting anything. 1 over r squared will really be important in determining detection distances for the verification parts of your project. And it's very easy to neglect, but you do so at your own peril, the problem of background radiation as well. Look at the 185 and look at the 1000 from the uranium. What are the sources of natural radiation that you might be detecting in those same energy bands? What are the sources of background radiation at the surface of the Earth if you're doing gamma ray detection? Give any examples? We talked about it a little bit, didn't we? Bananas. You know that, yeah. So what is it in bananas that? It's the potassium. Is the typical thing, but potassium's everywhere, right? But yeah, potassium, bananas. I don't know bananas. Yeah.
I heard that question.
I don't know. I saw somewhere that cream of tartar is like intensely high in potassium, but I just don't think you get cargo containers of cream of tartar coming in. So it's not just concentration, it's volume too. But yeah, radium and uranium in the Earth's crust, we talked about that in the first class. There's cosmic rays as well. There's cosmic rays causing cosmogenic neutrons at sea level. So background radiation is important. So you take your source term, you attenuate it by how far away you are from it and whatever the interacting medium is. Maybe we're underwater and its attenuation is going to be a problem. So you have attenuation, then you have solid angle, and then you have background. Those 3 things are really important. Those are the things that drive the detectability. So that's it. Enjoy the week off.